There's a lot of people from like Google here, Microsoft, other big companies, and you just kind of run into them and strike up a conversation. And yeah, lots of networking. And there's specific opportunities for women and people of color.
So hello and welcome to Embedded Track, where we'll be talking about how to put embedded C++20 into the web, just because it's Embedded Track. But no worries, there will be an assembly involved. We'll talk about how to deal with some low-level stuff as well, so don't worry about that. So hopefully no one will be disappointed after all, because we'll be talking about the web a lot. So hopefully that makes sense to you. So what we'll be talking about? Without further ado, let's begin. So the idea for this talk is coming from my nephew, who during the pandemic reached out to me and asked, I would like to try my microcontrollers, but due to the chip shortage, he couldn't get any. He was really excited about Raspberry Pi, like Pico, and wanted to buy it, but he couldn't. So he asked me is there anything I can do for him? I was like, did you try online? And he says, no, I didn't, but is there any option? He obviously didn't, he's 11, he didn't care about C++ at all. But he was worried, he was trying to figure out whether he can, start without getting the microcontroller first. So, it sparked an idea in my head that, well, what about, microcontrollers and online? What about C++20 and online? What about all of that? Can we actually do it? So, this talk is about that, the full story, how we came about that. So, we'll start from the motivation. I kind of give the gist about the motivation for the talk, but this motivation and the goal would be more about C++20 and my experiment that I've done and why it was successful or it wasn't. I don't know. Stay tuned. We'll take a look into tools and libraries, which I tried and explore. We'll implement a simple project using modern C++20, at least in my mind. And we'll go through the whole software cycle development process online, from the design, implementation, testing, benchmarking, and the simulation. The only thing which we are not going to do is to deploy to the microcontroller, because, well, that would be difficult, because I don't have one at the moment here. We'll do a small demo as well, with our learning, so hopefully that will clarify a lot of things, and it's kind of a nifty trick how we can do it, so hopefully you will like that. And we'll sum up. There are some slides about coding, and I find some more important than the others. So when there's dark blue background, it's not to wake you up, it's mainly to say something which is worth remembering, in my opinion. If you have any questions, by the way, please ask them. Don't, as you have them, no need to wait for anything at the end. So hopefully that makes sense and sounds as exciting for you as the experiment was for me. And if I forget, ask me about my nephew at the end, what has happened to that. Everything is powered by the Compiler Explorer, by the way. And not only, one of the tools. So, what's the motivation? The motivation is to, try them. Everyone knows what they are, more or less. Some of them are more fancy, some of them are more expensive than the others. The cheapest, I think, is the ATtiny, which is like, if you buy it in bulk, you can get it for like 20 cents. The Pico is also cheap. That's by Raspberry Pi 4 and Arduino Uno. The prices vary. Nothing is really expensive, But because of the chip shortage, nothing is really available either. So what's the problem with those guys? The main problem related to C++20 is the fact that, well, Arduino IDE, which is kind of the most popular IDE for microcontrollers, is supporting out-of-the-box GCC 7.3 and C++11. We can't do much modern C++ in a sense with that. Obviously, we can work around it if we install it, but online is difficult. And Arduino IDE is available online, but that's not the tool which we will go with. What about the simulation online? Are the tools available? Are they like, can I, simulate Raspberry Pi? Can I do stuff like that? We'll take a look what is available and what is not. But at the moment, the situation is not as great as it could be. And what about the modern C++? That's like the main, motivation for this talk regarding the coding. Wherever you see Arduino or these Lego C++ examples, all of them look more or less like that. A lot of global variables. There's a loop, and we have if, on if, and branches, and all of that is not really modern C++, and it's more C-like, and not really appealing to C++ developers as much, in my opinion. So what's the goal? The goal is to implement a simple project with C++20 for multiple architectures. So we'll take a look into Arduino, ATtiny, Raspberry Pi. So Arduino is based on 80 mega, so that'll be covering ARM, Cortex, and other CPUs. So we'll have wide spectrum of what we can do. And everything will be online, as I described. All the software development will be done with the online tools. We won't be doing the deployment because it's hard to do it online, and we don't have microcontrollers online available. But you can imagine that it could be possible if you have a farm of microcontrollers and a website in which you could just try it out. Arduino trying to do something like that, but at the moment it's quite difficult to get the hands on, Raspberry Pi online, which you could just connect to and play around. And all the tools are free. I think it's important to mention. So, it's my nephew, he's 11. He's 11, he doesn't care about, subscribing for anything. Why is he wanting to try something? So the same principle applies, even though we want to do it with C++20. So what tools we'll be going to use? For the design, we'll use PlantUML. Anyone is familiar with that tool? I see some hands. If you haven't seen it yet, hopefully I'll be able to encourage you to try it out. It's available online, in which you can describe different graphs, different UML graphs using text, and just get the image out of it. We'll take a look into the state machine one very closely. I think it's very powerful, especially that you have the text representation of what you want to represent graphically, because then you can imagine that you can push it to your repository and have sane merge conflicts on the text instead of images, if you wish. So development, sorry I couldn't use anything else than Compiler Explorer. The best tool available, I think. I personally believe that at the moment, because it has all the compilers, and we can have the cross-compilation, and we can apply and execute the code very easily, which we'll take a look into, and it's super powerful. So regarding the Compiler Explorer, that's the tools which we have there out of the box. So we have GCC for microcontrollers 11.1, and all the trunk version of anything else. And ARM will be for the ARM version of the microcontrollers. But also it's important that we have the GCC and Clang trunk available because we can write our tests also in the same kind of IDE with those guys without going to the ARM, so we can use fakes, which is pretty powerful. So this kind of is specific to Compiler Explorer. You can include a header file, and that was really important and relevant until a few weeks ago when the Compiler Explorer got an update where you can actually put multiple files and CMake into it. But before that, it was really hard to use libraries which weren't part of the Compiler Explorer, which you had to request and get the approval, and you could get into it. But if you wanted to try out, I don't know, your silly stuff or something that you experimented with, you could just do include and GitHub raw stuff, and we'll actually leverage that today. But the better solution at the moment is that you could use the multiple files and CMake and everything else, which is supported by the Compiler Explorer. Thank you very much for that. So implementation. For the implementation, I think we'll use the most powerful but really underused thing, which is really desired for the microcontrollers, which is the state machine. And we'll follow the UML 2.5, which is specified for the state machines. But personally, I believe that state machines are very well suited for the microcontrollers because of the states. We have the states and associated actions with them, which we want to interact with and change the state depending on some guards. And that's exactly what state machines are. And we'll take a look into our simple project of how easily that can be done and what kind of benefits we'll get out of it. If you want to read the spec, because there is a spec available for the UML, you can go to the website. It's pretty much the same reading as the C++ standard, so I don't know if you like it. To go to bed, we can always try. So, blue background, something to wake you up with. State machines might be easily identified. So all the online examples, in my opinion, with Arduino and others, when you like how to start with microcontrollers, will have something like that. Is button, something true. You have these Boolean variables, and when you have them, that immediately, if you know about state machines, you immediately know that something is wrong with the design here because it could be easily refactored with a lot of benefits to the state machines, and we'll take a look into that. And obviously, that's not a fix either, because that's very common, which we use instead of having multiple booleans, we just have in. So hopefully that will make sense after the talk, that why we want to avoid that and why that's not really a great solution for everyone. Simulation. For the simulation, we'll use this tool which is called Tinkercad, which I really like because it allows you to do this nifty trick where you can put assembly into it. I don't want to spoil the talk yet, but you can imagine that Compiler Explorer, assembly, Tinkercad, there is something going on there, and we'll take a look how to do it. But what is good about it? It does support online, it's free. It does support the following microcontrollers, sorry. 80 tiny, 80 mega, Arduino. It doesn't support Raspberry Pi because nothing does, sorry. At the moment if you want to play with Raspberry Pi, you just have to buy it, I guess. For the C# and Microsoft has this simulation which you can apply for, but it doesn't work with C++. So if you want a C++ and Raspberry Pi, well, go in line and try to get one. So there are multiple components that I pointed out. There are different microcontrollers available there as well. And we'll actually have the demo, so we'll take a look into how awesome it is. It's pretty awesome as well because it will show you, if you design it, it will show you what you have to buy. And you can go to the store and just buy it. So it will tell you, you have to buy Raspberry Pi, and you have to buy these resistors and this stuff. I don't think it's advertising its own store or anything like that. It's just a nice tool to have. Okay, so are there any questions related to what we talked already? Make sense? No questions about my nephew so far. He's still trying at that stage. So the idea here is to implement the simplest project possible. So I think the simplest is switcher or something like that, because what components you would use in order to start with the microcontrollers? I don't know, a button, LED. You connect button and LED. When you turn on the button, you get LED switch on, or something like that. That's my initial idea, and that's what I gone for. That's how I wanted to spark my nephew with online development. He actually used Scratch language. I don't know whether you've seen that one. It's really cool for kids. If you haven't, it's totally different than C++. Not even close. Okay, so I will describe. There's interesting news about that one. Sorry about that. Right now I'm curious. Anyway, moving back to our talk. We'll try to implement this switcher and describe the requirements using the Gherkin style, which is the BDD way of setting the requirements, acceptance criteria. So our project is to turn on and off LED when button is switched. So the first scenario we will try to cover is turn on the LED. So you can imagine that I have a board with a button and LED. That's something which we will provide with the Tinkercad. And that's something which we can buy in the future. So that will be the expensive part. Oh, come on, don't bother me here. And when then LED is, the button is switched off, LED is turned off, I switch the button, the LED is turned on. Sorry, I lost. Sorry about that. So, sorry. So we are here. Turn off LED. It's a very similar feature as the scenario as before. We just do it the other way around. When the button is switched on, and we have the LED turned on. When I switch the button again, the LED will be turned off. I hope that makes sense. So, does it? Very simple. So let's take a look into design. As I pointed out, we'll use planned UML for the design of the state machine. And that's the syntax for the planned UML. As I pointed out before, it's very similar to the UML 2.5 standard. It's kind of standard compliant. And the syntax looks as follows. The initial state is in the index square brackets with a star, and followed by the arrow to the initial state. And the transition itself, it comes from the source state to the destination state on specific event if the guard in the index bracket, square bracket, is satisfied. And when we follow, if that's true, we follow the action. And after the action, we change the state to destination state. So that's the way we write the code, basically. And that's what will be generated out of it. So we use the planned UML, we write this text, and this text will generate this picture. So how it will look plant UML in our example, we have to propagate start UML just for the sake to satisfy what it's about. We start in the off state. We go to the on state when the button is being pressed and it's on, meaning we press the button and the state is high. We turn on the LED and change the state to the on. And when we're in the on and button is pressed and button is off, we'll turn off the LED and go to the off. Otherwise, we won't do anything. Make sense? So that's the state machine generated. You can, you see it's very simple, but you can imagine way more complex state machines which will be to follow. So implementation, as I pointed out before, for the implementation, we'll try to use state machines. And we use a library which is called SML. I'm the author of it. That's why it was an obvious choice for me, but not only. There are benefits. It's C++ 14. It supports by all compilers, including Circle, if you've been on herp talk. It's UML 2.5 compliant, meaning I read the standard, and I actually implemented it to best of my knowledge. It's single header, which is important for the compiler explorer when I included it. It's 2,000 lines of code, so there's not much. And for the embedded world, what is important? No boost, nor STL is required. There's just single header. You don't have to have anything to start experimenting with it, which is very, very handy for embedded world. And obviously, because it's performance is critical for it. There are no virtuals or no RTTI things included in it. So it actually compiles with no RTTI, and it also compiles with no exceptions. Although exceptions are being supported if you want to throw them in the embedded world. So another reason why we would like to do it, don't look much at the left side yet, because we'll go through that. But I think what is important in the right side is what is being generated out of this code. So you can see it's basically 6 lines of assembly, which basically in the end just prints the LED being on, which is somewhere above. You can't really see, sorry about that. But there is an LED on lambda, which just puts on the screen. And that's basically what will happen because everything is optimized as we would like to with all the C++20. And that will be one part of the talk which we'll take a look into, that with the C++20 we can get better performance than with C. And why? One of the reasons why we will get better performance is because when we express what, if you've been on the herp talk, and not how, we can actually abstract the underlying implementation and get it to best performance possible. So there are different policies in SML which we can use in order to get the best performance possible. One of them is jump table, and all of that is regarding the change in the state and dispatching policy. So jump table is one of them, generated compile time. Nested switch, which basically generates a switch for you, and no macros involved, is another one. The trick here is just to switch again recursively in the default statement based on the argument packs and expand one by one. If else is yet another solution. Fold expressions, that's C++ 17 as well. Coroutines, yes, we can use coroutines to implement the backend as well. Why not? It's a bit different because the state is not being stored as a member, right? Because we cannot store an enum because it's flow, which we store with the coroutine context, but we can do that with SML as well. All of them have pros and cons regarding the performance, but regarding the performance, the best advice ever is just measure always measure. But if you can switch easily, then it's much better. Another benefits of using declarative way of state machine is the fact that we can get login out of the box, we can switch policies and get the performance out of the box, and others, which we cannot use if we couple ourselves to the specific if-else implementation, for example, as I pointed out in the beginning of the talk. So let's quickly take a look into benchmark. So I implemented the same simple state machine with different solutions. Enum, variant, SML, MSM from the Boost, and state chart from Boost. And all of them have, it's not really a biased benchmark, but somehow SML is the best. Surprise, surprise. But, the idea here is that to show that being expressive doesn't mean being slow. So SML actually is faster than the switch and enum. And there are reasons for that. And the size, because the optimizer can see more, and we give better hints than the switch statement, because we know more about what we want to optimize. So wherever you can give the better hints to the compiler, you help it to optimize the code better. And memory usage is something important in the embedded world, so it's important to minimize it, as well as the executable size, which is the same, minimized. And the line of code is something which you, in the end, want to optimize for, because it's always regarding the fact that you want to be productive. So I implemented enum switch without macros. So that was 300 lines of code. If you implement that with macros, probably less. But I would argue that it's less. It depends how you look at the macros, because it's still text substitution. So the compilation times, I have to point out, there is always penalty for using abstractions. Pointed out no zero overhead abstractions, but it's close to zero as possible. It's slower than enum, but well, take a look into MSM EUML. It's very nice abstraction, but it compiles 1 minute, 15 seconds in comparison to 100 milliseconds for the switch. I don't know whether you want to change just for that. I wouldn't. So let's take a look into the implementation quickly. We'll start with the concept, because it's C++20. Is anyone not familiar with the concepts? No one wants to admit, but I believe that the audience are really well suited for the talk. So I will go quickly with the concepts either way. So we'll have the concepts which have the setup on and off, and the two implementations for that component. One will be LED, where the setup will be just setting the pin mode, like in embedded world you do, for the output in that case, and on lambda will put that pin into the high state and off in the low state. And button will be very similar. It will be just on top of that the pressed function which will read the pin state. Make sense? And the auto pin is just the pin on the board where we have to put the component at properly when we wire it. So concept quickly: type constraints, act like documentations, better error messages, because we get it from the point of instantiation, not from the library code. Good for the experience. Claim to have faster compilation times. Haven't seen that yet, but potentially. And the syntax is very simple. We have concept. That's the weakest concept you can think of. Always true. Auto is also considered the weakest concept. Therefore, we can write full auto, which is the template, basically, which doesn't have any requirements. And that's the equivalent syntax for trying to propagate weakest concept possible, meaning there are no requirements on the type. So we either pass auto-arg, or we do the full shebang with the requires can be on the left, on the right, might be instead of type name or class, and might be also the short tear syntax with auto-arg as well. So we pointed out this diagram before regarding plant.uml. What about the implementation? That was the implementation from the plant.uml text syntax, and that would be the implementation from the SML syntax, because we want to express what, not how. Transition table will be, as you see, expressed basically the same way. We follow the UML standard in which the state is at the end, but there is a syntax in which you can write off equals on and follow with the event. So the only boilerplate here is the plus and the event, everything else, and the underscore s. A bit of boilerplate we have to put on, but not much. And as you can see, that UML and plant.uml and the C++ implementation is very close to each other. And you can actually go from one to another, so we can generate the diagram from SML as well, which is very handy and very easy because the syntax is very similar. So I hope that looks good and it's encouraging to you. And what will be generated under the hood, because all of that are types, is depending on the policy. And you can imagine that it will implement the switch for you or any dispatch policy you can imagine. It will implement coroutine if you desire. And that's the power of declarative design, because we don't express what, we express what, not how, which is great, in my opinion, because that makes the code loosely coupled and easy to change in the future, because we are not coupled to specific implementation. So, are there any questions regarding what we've heard so far? I don't see any. So let's move on. So we have a switcher, which is the state machine implementation, which injects the components, the button and the LED in that simple example, but you can imagine that we will inject tons of parameter pack arguments into it. And then we try to do the setup, and we'll do this nifty trick because we can use it with the C++20, where we immediately invoke function expression, in this case the lambda, with the familiar C++20 syntax when you have the class TSS immediately after the capture, and we can call setup on each of the components. So you can imagine that we call button : setup, LED : setup, and that would be difficult if you have multiple ones. Like it would be tedious to just write it, but you can separately. So with this nifty trick, we can just make it transparent to us. And then we implement the call operator for the transition table. As pointed out before, transition table is the same as the planned UML implementation. So no surprises here, I hope. We start in the off. We go through the event when we press the button and it's high state. We turn on the LED, we go to on, and vice versa, the other way around. So just a recap about, and is it blue for you? It's blue here. So that's the blue background I was talking about, if you haven't noticed it yet. So like in the embedded world, immediately invoked function expressions are very handy for the unrolling. So you probably know the pragma for unrolling, blah, blah. You can do it the same with C++20, with the unroll, for example, function here. If you want to unroll 2, and you just put the lambda expression with, which just prints CppCon 2021, that's the assembly you will get out of it. So it's fully unrolled for expression, for loop, which is pretty handy. What is even more handy in the embedded world is something like that, where we can immediately invoke function expressions in order to, in case of when we are in the C++ const eval word, meaning compile time word, we can just use fold expressions and not care about it. But in the runtime word, and that's line 17 when we do static assert, we go through line 5. And in line 20, when we pass runtime arguments, argc, for example, and therefore we cannot go through the const eval, we'll go through this handy lambda, which will expand over argument pack with the assembly, inline assembly. So that might be nifty trick for some of the embedded world when you try to generate a lot of things using assembly because embedded. So immediately invoked function expressions are very handy to do that inline. Obviously, we could do that before, but C++20 makes it easier. So what about testing? So testing is important, and we should always start from it. Even in the embedded world, TDD, it's possible, and we'll take a look into how can we do that with the compiler explorer. But in order to implement it, we can use fakes. And that's the basic principle, because it's really hard to do TDD, BDD with the hardware, because we don't want to burn it. And it depends how expensive is it. Some of it we can afford, some of them, well, it depends. I'm not judging. I don't want to burn anything. But I can burn some cycles using compiler explorer and testing. So we'll use a simple testing framework in order to fake button and fake LED. You can imagine they have implementation for the fake. We create a state machine, and we can easily verify if the state machine implementation, whether we are in the state or not. So by default, we start in the off state, and after that, we process event, because that's the interface API for the state machine, with the button being pressed, meaning the event is button pressed, and it has the high state, and when we change the state, we press again, and we change the state again, and we will go to the other one. Make sense? Easy to follow, easy to start with. It's really easy to test, much easier than testing all the underlying branches in the nested if or switch statements. I would argue that. And what about the main? Because that was the, so far we've written everything for the testing. For the production, we'll unfortunately have to do some macros to get the proper values for the boards, because they are different. We can abstract it somehow. We can easily abstract it using and verifying which microcontroller we are compiling for, and there will be different numbers because we wired it differently, or they cannot have the same values. And then it's just infinite loop, in which SML has this nice property where you can get all the events which can be processed by it. In that case, button pressed. So we can get out of it and use the same immediately invoked function expression to process events, which can be handled depending on what we have. I hope that makes sense. So what's about the benchmark? Are there any questions regarding the implementation? I don't hear any. Makes sense, I hope. So that's when my nephew stopped paying attention. I hope, I don't know, should I take a break? Anyway, obviously he didn't care about that because he uses Scratch. And I was saying, look at that, like how awesome is that? And yeah, Scratch is still more awesome than that. So that's the basic implementation of what you can find with, if you Google Arduino microcontrollers introduction LED button, let's say. And What is important here, we have like the global variables, which I pointed out before, that is a hint that we're supposed to have state machine. And we have this if LED state, if button state, blah, 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 change the state, change the pin mode, the stuff on the LED, on the button. And on the right side, we'll get 44 lines of assembly. I'm not wanting to claim here that less assembly is always faster, but in that example, because that depends on the instruction you have and pipelining, blah, blah, blah. There are reasons to think that smaller assembly might be faster, but that necessarily has to be true. But in our simple example, that's true. So that would be like C++03 implementation. If we refactor that and notice that we will get out of the global variables and we move them in place, meaning we'll put them on line 22, for example, we'll get a bit better performance, 32 lines of assembly generated because we limited the scope, so it might be optimized better. It's always good to limit the scope. And finally, we'll go to our implementation. And the policy here will be not specified, meaning that default will be taken, and the default for GCC will be the nested switch in that case. Sorry that it's not clear out of... if you wanted to specify the policy, we would put it on line 55 when we define the switcher. We could say policy, jump table, or whatever, and that will generate different assembly. But that's the fastest assembly, which has the less instructions. And that was the switch statement. So if you sum that up, I'll do it for you. Assembly, lines of code, C++03 with globals, 44, C++03 without the globals, 32, C++20 with a simple state machine, way more expressive, 24. And we could easily get to 32 if you wanted, just by switching the policy to if-else, for example. We could also implement it with the switch potentially and get better implementation as well. We will take a look into that at some point, but if you wanna, and you don't trust me because why would you? You can go and click it and see yourself. But I think while it's doing that and while it's doing any performance, I think it's really important to always measure, but it's not always measure whatever, always measure in the production-like environment, and the closer to the production setup you have, the better for the numbers you'll get, because otherwise micro-benchmarking probably won't give you the right number, and going through different production environment. If you want to, check out whether the Raspberry Pi code will work on ATtiny after recompiling the same performance, with the same performance, I would argue that probably won't be the case. But there's no silver bullet, and in my personal opinion, keeping all options open is always the best. So, for example, in that case, having the policies which you can switch easily is the best bit, so that we can experiment, run different benchmarks, and see which one actually gives us the best performance. So what about the simulation? I was saying about that at some point that we'll use this nifty trick because it's hard to do it otherwise. So if you use Tinkercad and it's basically Arduino kind of example, you always have a setup function and a loop function, because that's the way you implement microcontrollers. So the loop function is where the logic happens, but it's really difficult in Tinkercad, for example, and the online simulation tools, to inject all your online modern C++20 libraries and code, because they do not support that, because they're based on AVR GCC 7.3. So what we can do instead, we have Compiler Explorer. What does it mean? We have assembly. We can just do that. We can go to the compiler explorer, get the right side of it, copy the assembly, paste it into assembly, and be good. And we'll see that actually it does work. So, for example, that would be the example for Arduino. And you can see the right-hand side, and I will try to copy it while we'll have a few minutes. So that's the example for 80 mega, I think 32 or something, which is taken from the compiler explorer directly, copied into the assembly code, and then we'll try to execute it in a second. I was talking about these components, which the website will give us as well. So what we need for that. It doesn't show you here the prices, but you can go to the store. 80tiny, the same thing, just different assembly, copied from a different tab in Compiler Explorer. Still works, as we will see in a second. A bit different components, because of different microcontroller, cheaper, much cheaper. As I pointed out, this one is for a few cents if you buy it in bulk. And that's what I advised my nephew to do. He didn't, but that's a different story. And what I've done, so in order to, sorry because I didn't present it this way, because my Kindle actually broke just before the conference. But I wanted to present it from Raspberry Pi 400 using Kindle. And what is this project about? It's actually a microcontroller which talks to the Kindle wirelessly, and you can have the terminal and everything. And actually, I implemented this project on this environment because it was so cool. So I just did it. And you can see here is the LED, which I tried to execute. And it's pretty cool because Raspberry Pi 400 is ARM-based, so we can just compile it. We don't have to do the trick with the assembly because we have the executable. So if you want to be encouraged and by it, I hope that'll do it. So I know you were waiting for me screwing it up, so let's try it. Oh my gosh. That's always the scary part. But I prepared myself. So, sorry, are there any questions regarding anything we talked so far? No? Meaning nothing is clear? Or everything is clear? I hope the latter. But let's take a look. So that's the implementation for the planned UML. We go to the website, which I can't read, planneduml.com. Surprise, surprise. We go there, we put the text, and we get the image out of it. Very simple. That's the way I explored the design area. Didn't took me much because it was very simple. But you can imagine that having the text, as I pointed out before, you can put it in the Git and version control it and have a sane merge request whilst doing that, and still have the look at the image afterwards, which you can print or put on the board. So that's super cool in my opinion. Let's take a look into the code. So anyone is not familiar with that website? Of course not. Everyone is. What is super cool here that we have different compilers. So you can see GCC 11, GCC 11 for different architecture. So we specify 80 mega here. Here is, I would expect 80 tiny or something. Yeah, 80 tiny. GCC trunk. And that'll be the tests, and you can see here that all tests are passing, which is super cool because in this I would call IDE right now, we can execute the tests We can start with the TDD, we can implement everything here and get the different output for different compilers and see that all of them are compiling and working. And yeah, that's the implementation. There's nothing really surprising here. As I pointed out, we used this trick to include a header file from outside the world. We have some fakes, but besides that, it's all what I've shown before. Okay, let's do the demo. So let's first try to run it. So that's for the Arduino. Nothing happened. Expected. Okay. Woohoo! LED actually turned on. Turn off. Turn on. You see the pattern in the state machine? Where are we going? Which state is on? Off. On. Off. And the code for it. So if you stop, it's looking like that. And we have a few minutes. Let's do an experiment. If I will see something. Actually, it has main, doesn't really matter, all these labels. If you remove that, I see almost it. And we start the simulation again. Well, it doesn't work. It did compile though. So if you copy it, and that's, which one is that one? It's Arduino, so it's 80 megabase. So we copy that. Let's try to copy that into this code somewhere. Looks smaller. Ooh, it did work. If we copy something else, though, test-driven development, you have to have the red face. So let's copy this guy into it. And it's supposed to say something somewhere. Doesn't work, but I don't see the error. Well, not everything is perfect. There is an error somewhere, which I can't find right now. It might be in a serial monitor or somewhere. If I do another error. Oh, actually it pointed out. There is some hope. Anyway, it didn't work, so the assembly didn't work properly. It should say that RCall are not available on that Arduino, because I think it isn't called. But well, you get the gist. The idea here is that anyone can easily explore and connect a few dots with everything that's available here. Like you can drag and drop what you want, pin it, like connect it with anything. No really huge knowledge required. And we have the last demo, which is 80 tiny. You see the pattern here is the same, copied from Compile Explorer. Start the simulation. No, battery has to be on. We need the power. But notice that 80 tiny requires just 2 AAs. So, not much. So, yeah. that will be the demo. And I think we don't have much time, so I will sum it up quickly. So hopefully that was encouraging. And I think the experiment that I've done for my nephew shown that the online tools make the embedded development with modern C++ possible, or at least easier. Not everything is easy, not everything, like you notice this copy in assembly, could be easier, but it is possible. And Raspberry Pi would be nice to be able to simulate. Would be nice to have the newest and greatest compilers. But yeah, that's where we're at. And also an important fact is that state machines can be really expressive way to represent the application flow, especially good for the embedded world. And because they express what, not how, we can easily change the underlying implementation. We can optimize it and hint compiler into getting the best out of available tools and boost performance with that. So with that, let's embed all the things with C++ 20. Thank you very much.